This is part 3 of the series Quadrilaterals. We're continuing this part with a discussion of the parallelogram consecutive angles theorem. If a quadrilateral is a parallelogram, then the consecutive angles are supplementary. So angle A and B are consecutive angles, and it's easy to see since these are two parallel lines. This AB is cut by a transversal. We know that the consecutive interior angles are supplementary. Also, we can see that AB is parallel to CD, and AD would then be a transversal, so angle A and D are consecutive interior angles, and they would be supplementary. The same is true for C and D and for C and B. So that's as far as we need to go with this proof. The issue is that in a parallelogram, the consecutive interior angle pairs are all supplementary. Let's go ahead and put this into practice and work a quick example before we move on. In this problem, we want to find the measure of angle B given the measure of angle A. Angle B is supplementary to angle A, and so we take 180 minus 51 equals 129 degrees, and that's the measure of angle B. And the same thing would be true of angle D because those two angles are congruent, and angle C would be 51 because those two angles are congruent. So let's go ahead and move on to the next section. The next property of parallelograms is given by the parallelogram diagonals theorem, which says if a quadrilateral is a parallelogram, then the diagonals bisect each other. So if we draw diagonals from non-adjacent vertices, we can see here that it says that this segment is congruent to this, and this segment congruent to that. So let's go ahead and take a look at this proof and see how that works out. Because we have to show that AX is congruent to XC, proving that X bisects AC, and that BX is equal to XD, showing that X bisects BD, we're going to try and prove these two triangles are congruent. And what I see starting off is we have some alternate interior angles here. We have vertical angles, and we know these sides are congruent by the parallelogram opposite sides theorem. Remember that every time we've proved a theorem, we can then use it in another theorem. So that's the general strategy for our proof. So let's go ahead and get started with this. First thing, we'll take care of the side. So we can say AB is congruent to DC, and that's parallelogram opposite sides theorem. So that gives us this side is congruent to this side. Now let's set this angle equal to that angle. So angle AXB is congruent to angle DXC. That's the vertical angles congruence theorem. And then we'll set this angle equal to this angle. So these are now congruent. And then we can say angle BAX is congruent to angle DXC. And that's alternate interior angles theorem. Need to give ourselves a little bit of space, and so we know this angle is congruent to this angle. Now these two triangles are congruent. We can say triangle ABX is congruent to triangle CDE x, and that's angle, angle, side. Angle, 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 side. So angle, angle, side, congruence theorem. Now we can say the final thing, this side is congruent to this side, and this side is congruent to this. So that's our final statement. AX is congruent to XC, and BX is congruent to XD, and that's CPCTC. Corresponding parts of congruent triangles are congruent. This part corresponds to this, and this corresponds to that. So now we know that this bisects both of those sides, and we're done with our proof. As a side note, when we switched over to using the vertical angle here, I just did that because vertical angles jump out at me, but it would have been perfectly possible to just use this angle, this angle, this angle, and this angle, both because they're alternate interior angles. Just remember that there's rarely only one way to execute a proof, and this was just one of those ways. So just because you may not have gotten the same results as me doesn't necessarily mean that your result is wrong, and my result is certainly not the only way to do it. So just wanted to throw in that additional note. Alright, let's use this in an example and see how that goes. In this example, we're given a parallelogram in the coordinate plane, and we're told to find the intersection of the diagonals of the parallelogram. Well, given the theorem we just learned, we know that the intersection of the diagonals is going to be the midpoint of both of those diagonals. So that's all we need to do is find the midpoint of these, and we will have our result. The midpoint of OM is going to be given by 7 plus 0 over 2 and 4 plus 0 over 2. That is the average of the x's, 7 and 0, 4 and 0, the average of the y's, which gives us 7 halves and 2. 7 halves and 2. If we did the same thing for ln, we would get L is 1 plus 6 over 2 and 4 plus 0 over 2. 1 plus 6 is 7 over 2. 4 plus 0 is 4 over 2, which is 2. And they come out to be the exact same coordinate. Let's just go ahead and draw in those diagonals and see how this looks. So we'll draw these diagonals in here. And the coordinate should be 7 halves, which is 3 1/2, and 2. And that looks just about right. So it looks like we did a good job. Alright, let's do one more example and see how that goes. In this example, we're given 3 of the 4 coordinates of a parallelogram, and we need to find the 4th coordinate, the coordinate for vertex y. So first thing, I'm very visual, so I'm going to go ahead and draw in these existing line segments. Alright. Now, we know, based on the properties we've learned from parallelograms, that XW is going to be parallel to YZ. And we know that WZ is going to be parallel to XY. So the new line is going to have the same slope as this WZ here, if we draw from here to here. Or we could draw from here up and make it parallel to this. It really doesn't matter one way or another. Going from here to here, we have a slope of -1, 1, 2, 3, 4, 5. -1/5. That means if we go down 1, 2, 3, 4, 5, this should be our target point. So I made a little mark there. Now from point X, we're going down 1, 2, 3, 4, 5, 1, 2. So negative 5 halves. So if we go down negative 5 halves from here, we should end up at Z. 1, 2, 3, 4, 5, 1, 2. And it works. So that is our coordinate. Our coordinate becomes 2, 1. Okay. And now on to the next section. The next property is presented in the parallelogram opposite sides converse theorem. If both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So here we have AB is congruent to CD, AD congruent to BC. The theorem states this has to be a parallelogram. Let's do the proof and see why. I've gone ahead and written in the given. And the plan for our proof is very, very similar to ones in the past. I'm going to create a triangle by inserting a segment AC here. And we're going to try and prove those triangles congruent. And it looks like we can do that by side, side, side. Then we're going to attempt to show that we have some congruent angles inside here, which will allow us to show that AB is parallel to CD and AD is parallel to CB. Let's get started and see where this leads. First thing, I want to draw in AC and write our statement as usual. So draw AC. There is one line. Now, we're going to say that AC is congruent to itself. So AC is congruent to AC, and that's again reflexive. Property of segment congruence. So this is congruent to itself. Now we know these two triangles are congruent. So triangle A, B, C is congruent to triangle A, D, C, and that's by side, side, side congruence. Now that we know that these two triangles are congruent by side, 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 we know that BAC is congruent to ABC, and this angle, DAC, is congruent to BCA by CPCTC. So this congruent to this, this to this. That leads us to the fact that we have two lines cut by a transversal so that the alternate interior angles are congruent, and two lines cut by a transversal so that alternate interior angles are congruent. That means AB is parallel to CD and AD is parallel to BC by the alternate interior angles converse. So we've proven this side is parallel to this and this parallel to that. That then tells us that this must be a parallelogram by the definition of a parallelogram. Parallelogram is a quadrilateral with two pairs of opposite parallel sides. And so that is our proof. If you would like to go back through this in case you missed a little bit, feel free. That is our proof, and we're on to the next section.